In the last episode, we saw a matrix as a transformation of the whole space. Now we attach one number to that transformation, the determinant. Geometrically, the determinant measures how the transformation scales area in 2 dimensions or volume in 3 dimensions. If the determinant has absolute value 3, every area becomes 3 times as large. If the determinant has absolute value 1/2, every area is cut in half. The sign adds one more piece of information, whether orientation is preserved or flipped. The easiest way to see a determinant is to start with the unit square. Before the transformation, the standard basis vectors form a square of area 1. After the transformation, those basis vectors land on the 2 columns of the matrix. The original square becomes a parallelogram spanned by the 2 column vectors. Because the original area was 1, the new parallelogram area is exactly the area scaling factor. That scaling factor, with a sign attached, is the determinant. For a 2 by 2 matrix, the determinant is often written as a D minus BC. That formula is not just a trick to memorize. It is a compact way of computing the signed area of the parallelogram made by the 2 column vectors. One diagonal product contributes area with one orientation. The other diagonal product subtracts the area that points the opposite way. When you remember the formula, attach it to the picture. 2 transformed basis arrows enclosing oriented area. The absolute value of the determinant tells how much area is scaled. The sign tells whether orientation is preserved or reversed. Imagine walking around the unit square in a chosen direction. If the transformed parallelogram keeps the same turning order, the determinant is positive. If the transformation flips the square like a mirror, the turning order reverses, and the determinant is negative. So the determinant is not just area, it is signed area. A determinant of 0 has a very concrete meaning. The transformation collapses area to 0. In the plane, that usually means a 2-dimensional region has been flattened into a line, or even into a single point. Once that happens, different input vectors can land on the same output. The transformation has lost information, so it cannot be reversed uniquely. This is why determinant 0 is the geometric signature of a singular matrix. In 3 dimensions, the same idea becomes volume. The 3 standard basis vectors form a unit cube. After a linear transformation, those 3 vectors become 3 new edge directions. The unit cube becomes a skewed box called a parallelepiped. The absolute value of the determinant gives the volume of that new box. So whether we are in 2 dimensions or 3, the determinant measures how much space has been expanded or compressed. The determinant also behaves beautifully under composition. If one transformation doubles every area and a second transformation triples every area, doing both makes areas 6 times as large. That is the geometric reason behind the rule det of AB equals det A times det B. Even if the transformations include rotation, shear, or reflection, the total sign scale is the product of the sign scales. The matrix product may depend on order, but the determinant of the product records the compounded area scale. This gives us a quick test for invertibility. If the determinant is not 0, the transformation has not collapsed area or volume completely. Every small region still has non-zero size after the transformation. That means the transformation can be undone by an inverse matrix. If the determinant is 0, some direction has disappeared into another direction. Then there is no unique reverse path. So det A not equal to 0 is not just an algebraic condition. It means the space has survived with its full dimension. Now return to the equation X equals B. If the determinant of A is non-zero, the transformation does not collapse space. Every output target has exactly one input that reaches it. But if the determinant is 0, the output space has been flattened. Some targets are no longer reachable at all. Other targets may be reached by many different inputs. That is why determinants appear in discussions of whether a linear system has a unique solution. Here is the core picture to keep. The determinant measures how a linear transformation scales area in 2 dimensions and volume in 3 dimensions. The absolute value gives the scale factor. The sign records whether orientation is preserved or flipped. A 0 determinant means area or volume has collapsed completely, so the transformation is not invertible. For linear systems, a non-zero determinant means every target has one input. A 0 determinant means reachability and uniqueness can fail. In the next episode, we will generalize this idea into rank, column space, and null space, which dimensions survive, and which directions disappear.